The ozone layer protects us from UV light, especially UVB, which causes skin cancer. UVA penetrates through and comes to Earth, but UVB stops here and destroys the ozone layer that is trying to stop it. Now let's just look at how this destruction takes place. Ozone is 3 atoms of oxygen bonded together. So when they are being bombarded by UVB, they break into a molecule of oxygen plus a free radical of oxygen. Free radical is a species with a single electron. Now this free radical is extremely destructive, destroys another ozone molecule, and in the process now you form 2 oxygen atoms. So this is a chain reaction that the ozone layer gets depleted. Now what you need to do in IB as of this year for the new syllabus, you need to also be able to calculate the energy that you need or the wavelength that you need to break ozone compared to oxygen molecule. If you look at ozone, the Lewis dot structure for one of the resonance looks like this, and then you show the other resonance by traveling that pi electron to other side, so you delocalize it. And if we ask you to talk about the bond length and bond strength, you're going to calculate something known as bond order, which is number of bonds divided by bonding position. 1, 2, 3 bonds divided by 2 possible position. The bond order is 1.5, indicating your bond length and strength are between single and double. And the bond enthalpy actually for oxygen in ozone is 362 kilojoules per mole. Now if we compare it versus oxygen, oxygen diatomic has 1 fixed double bond, so the bond order is really 2 bonds divided by 1 possible position, which is 2. If bond order is bigger than the other one, indicates your bond is stronger and shorter. And actually when you look at your data booklet, the bond enthalpy for oxygen in this case is 498 kilojoules per mole. The high energy indicates you need smaller nanometers of a wavelength of a photon to break it. So this indicates you need higher energy, higher frequency, and lower wavelength for that photon. Now let's just calculate the actual wavelength of the photon that we need. So for ozone, we are going to approach it. First, I'm going to convert the kilojoules to joules. So you have 362,000 joules per mole of ozone. Now we have to find for one molecule to talk about one photon. So remember, this is equal to 1 mole, is per mole. And in 1 mole you have 6 times 10 to the power 23 molecules, and here I'm just going to say for each molecule I need 1 photon. Therefore let's find for 1 photon how much energy do I really need. So after you cross multiply, you will find the energy needed to break ozone bond is actually equal to 6.0 times 10 to minus 19 joules. Now energy of a photon, if you remember from your last topic, is also Planck's constant times frequency. Planck's constant, you look it up, it's 6.63 times 10 to minus 34 joules times second. So when we put all these things in, frequency is energy divided by Planck's, and frequency comes to be 9.1 times 10 to the power 14 second minus 1 or hertz. In order to find wavelength, we go after another constant. Speed of light is equal to wavelength times frequency. So wavelength is simply equal by speed of light divided by frequency. Speed of light is 3 times 10 to the power 8 meters per second. And after you apply this, the wavelength turns out to be 3.3 times 10 to minus 7 meters. Now remember, 1 nanometer is equal to 10 to minus 9 meters. So after this, we convert it into nanometers, which is about 330 nanometers. So this is the wavelength of a photon that you need in order to break one of these bonds. So you need about 330 nanometers, which is UVB. That's the amount of energy they usually carry. Now let's do the same calculation for oxygen. How much do we need? We are hoping we get a smaller wavelength than 330. So same notion, the energy is equal to 498,000 joules divided by Avogadro's, and that becomes 8.27 times 10 to minus 19 joules per photon. Now energy was equal to Planck's times frequency, so we can apply that, and frequency turns out to be 1.25 times 10 to power 15 second minus 1. Speed of light is frequency times wavelength, so we can apply it now and find wavelength is equal to 2.4 times 10 to minus 7 meters. In order to convert it to nanometers, we remember 1 nanometer is 10 to minus 9 meters. So finally, wavelength is 240 nanometers. So you need a smaller wavelength to break this double bond here, which is 240 nanometers. Smaller wavelength indicates you have a higher frequency, which indicates you need higher energy of photon. So this is something that bonding is going to help you. Ozone layer is very important. Pollutions such as carbon fluoros, they also destroy ozone layer.